Of course, what this means is that when S looks at S prime's clock, S will say that S prime's clock is running slow. But it works both ways. S prime can look at S's clock and say S's clock is running slow. How can that be? How can S say that S prime's clock is running slow and S prime say that S's clock is running slow? It doesn't seem to make sense. I know, let's get this sorted out once and for all. Let's arrange for S prime to double back, land on the top of S, climb down through the little porthole, and then they can actually look at one another's clocks and see what's going on. But I'm afraid that's not going to work, because the minute you double back and land on the top of S, you've slowed down, and that's an acceleration. And special relativity doesn't cover the situation where you slow down. You'd have to go to general relativity for that. But in fact, you can show that clocks slow down. Experiments have been performed with fast-flying aircraft and very precise clocks to show that there is a slowing down of time. Of course, unless you get to very, very high speeds comparable to that of light, the clock isn't going to slow down by very much, but it does slow down. Now let's look at what happens if S and S prime are observing a particle, or anything else for that matter, moving at a certain velocity. Let's suppose the particle is moving on the S's frame of reference. And let's suppose that it is travelling, as far as S is concerned, at velocity v. V will simply be x, the distance travelled, divided by t, the time taken. S prime, however, observing from his spaceship, which is of course travelling at speed u relative to S, will measure a velocity of that particle of w, which is equal to x prime, the distance which S prime measures, divided by t prime, the time on S prime's clock. So w equals the speed of that particle as far as S prime is concerned, which is x prime over t prime, which is x minus ut divided by t minus u over c squared x. The gammas in each case will cancel. If we divide all those terms by t, we get x divided by t minus u divided by 1 minus u over c squared x over t. But x over t is simply the velocity measured by S, v. And so we get that w equals v, the velocity measured by S, minus u, the relative speed between S and S prime, divided by 1 minus uv over c squared. And similarly, it works the other way, that v equals w plus u, divided by 1 plus uv over c squared. If, of course, w equals c, if something is actually travelling at the speed of light, the formula is v equals w plus u divided by 1 plus uw over c squared, and that equals c plus u divided by 1 plus u over c. And that equals c. And that's the result of the Michelson-Morley experiment. It doesn't matter what the relative speed is between S and S prime. If a particle is travelling at the speed of light on S, it will also be measured as travelling at the speed of light by S prime, irrespective of what the relative speed is between them. We now move on to a concept called time dilation. Let's take an event that takes place on the S's frame of reference. And let's suppose that its duration is t seconds. Now S is entitled to claim that he is stationary, and that therefore there was no distance travelled. X is therefore 0. What does S prime say? S prime says that T prime equals T, which now we know is capital T seconds, minus U over C squared times X, divided by the square root of 1 minus U squared over C squared. But X is 0, and so T prime equals T divided by the square root of 1 minus U squared over C squared. We now move on to a concept called length contraction. Let's suppose that S prime has a rod of length L prime. S, travelling at a relative speed of U, measures that rod and says that it is of length L. Both have to measure that length at a time distance of 0. You can't measure one end of the rod and then go and have a cup of tea and come back and measure the other end of the rod, because then you'll get the wrong answer. You have to measure the two ends simultaneously. That way you will get the correct answer for the length. So S prime says that L primed equals L minus 0, since there is no time difference, divided by the square root of 1 minus U squared over C squared. In other words, L equals L prime times the square root of 1 minus U squared over C squared. And that means that a moving rod appears to be shorter. As you move, so the things that are not in your frame of reference get shorter. Their length contracts. The only length that appears to be correct is the length that's moving with you. Everything else appears to shorten. Now let's consider causality. If two events happen, event 1 followed by event 2, is it possible to see event 2 before you see event 1? Well, yes it is, very easily. Let's suppose that we have two stars. One of them is 8 light years away. The other is 2 light years away. On the first star, an event happened 4 years ago. On the second star, an event happened 2 years ago. Which event will you see first? Well, the answer is you'll see the event on the second star today, because that will have taken 2 years to get here, and we will see it today. The event that happened 4 years ago on the other star is still travelling. It will be 4 years before we see that event. So it's perfectly possible to see two events in the reverse order of when they happened. But what happens if one event caused the other event to happen? Can you still see the later event before you see the former event?